Our last units of concentration are parts per million and parts per billion. We use these for really tiny concentrations. Parts per million is equal to mass of the solute, that is the component, the small part, divided by mass of solution, the whole thing, times 10 to the 6. Parts per billion is mass of the solute over mass of the solution times 10 to the 9. These equations are very similar to our mass percent equation. Our mass percent equation would be mass of the solute over mass of solution times 10 to the 2. In other words, 100. With parts per million, we're multiplying by 1 million. With parts per billion, we're multiplying by 1 billion. In percent, the cent is referring to 100. So 1% is 1 out of 100. 1 part per million is the same thing as 1 out of 1 million. And 1 part per billion is the same thing as 1 out of 1 billion. If you had 1 billion molecules in your syringe, and one of them was the thing you were interested in, then it would be a 1 part per billion solution. Let's look at an example. The EPA has to test tap water to see how much lead is in it. If the concentration of lead reaches 15 parts per billion, then something has to be done to treat the water to remove the lead. We want to find the mass of the lead in micrograms that would be contained in a typical glass of water, which is 300 milliliters. We're also going to be finding what 15 parts per billion is in parts per million. We know that in the parts per million equation, we multiply by 10 to the 6. In the parts per billion equation, we multiply by 10 to the 9. Our equations are related by a factor of 1,000. 1 part per billion is 1,000 times smaller than 1 part per million. So we could use a conversion. 1 part per million equals 1,000 parts per billion. Therefore, 15 parts per billion is equal to 0.015 parts per million. We can use the density of water to convert between grams and milliliters of water. Since the density of water at room temperature is 1 gram per milliliter, that's a really easy conversion. If we have 300 milliliters of water, that means we have 300 grams of water. Since most of the solution is water, we can estimate the mass of the solution to be 300 grams. We're going to plug the numbers we know into our equation for parts per million. But first, we need to rearrange the equation to solve for mass of the solute, which is lead. When we rearrange the equation, the mass of the solute needs to be isolated by itself. To do that, we multiply both sides by mass of the solution and divide both sides by 10 to the 6th. Our rearranged equation becomes mass of the solute, which is the lead, equals parts per million times mass of the solution divided by 10 to the 6th. We plug in our 0.015 parts per million, which we solved for earlier, times the 300 grams of water, which is our mass of the solution, and divide by our 10 to the 6th, and that gives us 0.000045 grams. Notice we get grams because the mass of the solution is in grams. What we really want is micrograms, though. We're going to change it into micrograms by dividing by 10 to the minus 6. And that tells us 4.5 micrograms of lead would be in that 1 cup of tap water. A 50.0 gram sample of industrial wastewater was determined to contain 0.48 milligrams of mercury. What is the concentration in parts per million? Is it A, 48 parts per million, B, 24 parts per million, C, 9.6 parts per million, or D, 19 parts per million? The correct answer is C, 9.6 parts per million. Notice the masses are different. Just like with our percent composition problems, we need the units to be the same. We can either get the mercury into grams or the sample into milligrams. Once we get them into the same units, then we do the part divided by the whole and multiply by 10 to the 6th to come out with 9.6 parts per million.